we need to talk more about compounds then. And most people get the idea of compounds being like atoms that are stuck together in a repeating unit, but I don't know if all people know that actually there are two types of compounds. There are molecular compounds, they're synonyms with covalent compounds, and there are ionic compounds. So molecular compounds and ionic compounds. And I really encourage students to kind of make a list of the differences, and I'm going to try to kind of talk you through that. But one of the differences right off the bat is that if we have a repeating unit of a molecule, if we have a repeating unit of a molecular compound, then that repeating unit is called a molecule. But I would warn you that the word molecule is overused. If you have a compound that is actually an ionic compound and you have a repeating unit, you don't have a molecule, you have what's called a formula unit. So I'm going to kind of show you how physically they are different. There's repeating units of these two different types of compounds. So I know one more time I'm going to bring this in because I want to emphasize where we're at. Again, we're at the compound level and there are two types of compounds. So I encourage students to go ahead and start a little tally. And if you don't mind to stay consistent with what I do, over on the left we're going to put molecular CPD for compound, and then on the right we're going to put ionic compound. And we already have something to add to our list. So molecular compounds, the unit is equal to literally molecule. And for ionic compounds, if you have one unit, one repeating unit, you've isolated it, you have what's called a formula unit. Now there are other differences too, but this is the first difference. I'm going to try to show you what that looks like. So molecular compounds versus ionic compounds. You use chemical formulas for both of them, and I'm sure you've heard of both types. Another thing you can put on your list, and if I was you, I would just kind of have my tally, okay, going on. And what do we say? Molecular over here, molecular, goodness, an ionic compound. So here it says that if you have a metal, okay, anywhere in your formula bonded to nonmetals, but metals are the telltale site. If you have any metal, then you probably, in your formula, then you must have an ionic compound. Now, if you have no metals in your formula, then you probably have a molecular compound. And then you may need to know this if you're trying to identify your compound as either being molecular or ionic, that we have a lot of hydrogen compounds. Hydrogen is a non-metal usually for purposes of identifying whether your compound is molecular or ionic. So in other words, if you have hydrogen in your compound, that doesn't count as being a metal. So you could still have a molecular compound. All right? Very good. So that's something else to add. We're going to have to try to differentiate between these two types of compounds. So here we have the formula of a compound. Here's the formula, 2 nitrogens and 4 hydrogens. And here's the name of the compound, hydrazine. Let's see if this does anything for me. Whoop. Whoop. Oh, there it goes. Yep, that's about all it's going to do. It's going to wiggle back and forth. Okay, so the 2 nitrogens in the middle and the 4 white hydrogens, so the nitrogens are blue, the hydrogens are white. But my point here is you kind of see, do you see where it's got those, 6 atoms kind of have their own little thing going on? Okay, so that's a molecular compound. Ammonia, okay, again it's another type of molecular compound. We have 3 hydrogens and 1 nitrogen, 4 atoms that are bonded together. Nitrogen is clearly a non-metal. It's on the right of the jag. Let's see if this works for me. Okay, there's ammonia, NH3. Again, blue represented here is nitrogen, and then the white balls are the hydrogen atoms. Okay, so since those are molecular compounds, then we must have looked at a molecule of hydrazine and a molecule of ammonia. So these are all molecular compounds. So ammonia we just looked at. Water is an example of a molecular compound. Methane is an example of a molecular compound. Hydrogen is, we consider non-metal, and if you look for the metal, if you find no metals, it's probably a molecular compound. Carbon is a non-metal, nitrogen is a non-metal, and oxygen is a non-metal. So like you kind of saw in that animation, we definitely have, when you have a molecule of a molecular compound, you know which atoms are stuck together in that repeating unit. Okay, I'm going to kind of contrast this to ionic compounds here in a minute. Speaking of ionic compounds, so you probably would tell me that the formula for table salt is NaCl. There you go, NaCl. Of course, Na stands for sodium, and Cl stands for chlorine. So if you look for, are any, how do I say this? Is there a metal here? Yes, look at the periodic table. Your metal actually is sodium. Sodium is a metal. It's like a group 1A metal, okay? So the fact that you have a metal means that you must have an ionic compound, and you definitely have an ionic compound. So let's use this as an example to kind of see how those atoms get together, get bonded together. Let's see if this works for me.
When sodium and chlorine react, the sodium transfers an electron to the chlorine, forming oppositely charged ions. Although the compound has no net charge, its component ions of opposite charge attract each other to form ionic bonds. In turn, these ions are attracted to others, and an ionic solid called a crystal lattice is created.
So I think I actually bring this video in later because those gray things that you see, those actually are the chemical bonds that are connecting the sodiums and the chlorines. And this video actually went further in that it talked about electron being transferred. We're going to talk more about that electron being transferred also. Okay. One of the things I want to focus on though is, do you see where this forms what we call a crystalline lattice structure? And if you have your tally handy, over under the ionic compounds contain metals and are made up of formula units. Under ionic compounds, you could also form these crystalline lattice structures in their solid state. Is that not cool or what? Okay. I have another video about an ionic compound. The bottom one down there, so which of these is a metal? Okay, I'm telling you this is an ionic compound, so look for the metal. Which is a metal? Is it potassium or bromine? Of course, potassium's the metal. So let's take a look at the compound potassium bromide. See if you see any similarities with your sodium chloride.
A crystal of potassium bromide has a distinctive shape with perpendicular edges. This shape directly reflects the arrangement of the ions in the crystal lattice. The compound is composed of alternating potassium ions and bromide ions.
So again, in its solid state, do you see where, I think I can draw on this, dun dun dun. Do you see where if I were to go over here and to snag a green and how do I say, a green and red, I mean, I don't know which two atoms, well, I shouldn't say atoms, ions, which two potassium and bromines go together. It's a community. It's a commune. It's a crystalline lattice structure. Let's see if I can go back. So I kind of want you to get that idea. This is actually kind of what we've been talking about. You see here the crystalline lattice structure, kind of the blue or purple and green. Okay, so those would be formula units of sodium chloride. And actually down here, I think this is pretty cool too. The fact that that ionic compounds form these crystalline lattice solids actually gives us some really kind of neat facets, some faces to the material. This still is sodium chloride. Just kind of a look at, you can kind of see these nice blunt edges. Very pretty. Okay, so one last thing to kind of summarize. I'll put this whole slide up here, I think. Did you see where in those when an ionic compound is in that, like we call it a lattice? Does it look kind of like a lattice? It's kind of like stuck next to each other. I mean, the alternating ions, alternating colors. We never really know. Like I said, I put it which sodium, which chlorine goes with which. So, for instance, actually, there are 6 different directions that, in the cases that we looked at, that the ion can go to get the other ion. I don't know if that makes sense. But that's trying to show you the idea of a community. And if you were to isolate one repeating unit, you have a formula unit.